Okay, simple harmonic motion is an extension 1 concept. It occurs when a particle is moving in a straight line so that its acceleration is always directed towards a fixed point O and is proportional to its distance from that point. I'll explain that all later. Examples are a mass attached to a spring going up and down, the bobbing motion of a buoy, which is pretty much the same as well, how it just goes up and down, a pendulum swinging side to side, and the vibrations of a tuning fork, which would go like that. We're going to do this by example. So the first example we're going to look at is a particle moving in a straight line so that its displacement from the fixed point, which is the origin, in a straight line, so the particle moving up and down or sideways or whatever, at time t seconds is defined by this, x equals 5 cos 4t. We're going to draw displacement, velocity and acceleration graphs underneath each other using the same scale. We're not going to copy that bit on displacement yet. We're going to do our graphs first and then we'll come back and talk about the displacement. So we've got x equals 5 cos 4t and we're going to draw the displacement, the acceleration and velocity graphs. Now, before I do that first bit, I think I actually should have done it the other way round. Let's just come down here for a sec. So, displacement. Do you want to do that one first? Actually, we can do the values up here. So, we're going to have to write what these graphs are somewhere. So, the displacement graph is x equals 5 cos 4t. 5 cos 4t. If you want, you can... So when t is 0, what do we get, girls? Cos of 0, what is it? What's cos of 0? 1. Let's have, so therefore, what is the value here of x? So we know that x equals 5 cos 4t, so when... Sorry? No, it need to be in radians. Okay, look, what I'd prefer you to do is actually not even use your calc at the moment. You should know, I'm going to draw a simple cos curve down here. There's a cos curve, okay? Now, cos of 0 is 1. 5 times 1 is 5. Don't do the pi on 8 yet. Oh, well, you can. What's 4 pi on 8? Guys, you don't need a calc. I don't want you using a calculator. Isn't it cos of pi on 2? You just need this graph down here. What's cos pi on 2? 0. This is the cos curve. Guys, cos of 0 is 1. Cos of 90 or cos of pi on 2 is 0. So 4 pi on 8 is cos pi on 2. So it's 5 times 0 is 0. What about when t is pi on 4? It's 4 pi on 4, which is just cos of pi, which is negative 1. So 5 times negative 1 is negative 5. 3 pi on 8. So it's 4 times 3 pi on 8. 4 on 8. Is it 3 on 2? 3 on 2 pi? Guys, if t is 3 pi on 8, you get 4 times 3 pi on 8. What do you get? 3 pi on 2. What's 3 pi on 2? Cos of 3 pi on 2. Can you see from the graph? 0. And pi on 2, 4 pi on 2 is the same as 2 pi. Cos of 2 pi, 1. What do you think? Now, these are just going up by the same amounts. This would just continue. So what have we got for 5 pi on 8? Just checking the first one. 4 times 5 is 20 on 8.
Wait, Miss, isn't the first one 5 on 2? Oh.
Because cos of 0 is 1.
Yeah.
So 5 pi on 8 with, what do we get?
5 on 2.
Yep. Yep. So it just continues, guys. Once we've got one cycle, it'll just continue. Okay, and then we should have negative 5, 0, 5. 0, negative 5, 0, 5. 0, negative 5. So if you want, we can sketch the first displacement curve. Are we ready? So what did we start with? 5. So get your scale correct here. If that's pi, the middle's pi on 4, that's pi on 8, 3 pi on 8. So just put in your pi on 4 and you should be fine. And this would be 3 pi on 2. So when it's 0, it's 5. At pi on 8, it's 0. At pi and 4, it's negative 5. At 3 pi and 8, it's back to 0. And at pi and 2, it's 5. Now, girls, that was, you know what, me doing this table was a really long way. What would have been the best thing for me to draw this? Look at 5 cos 4t. We know the amplitude's 5, and the period is 2 pi on 4, which is, see, look here. Isn't the period 2 pi on 4, which is pi on 2? So I could have just come straight here now, and I think we'll do this for the others, and done that. Isn't that the easier way to do it? One full period, and then just keep going. So that's what we'll do next time, instead of all that. It doesn't matter. Good practice. Are we good? What's this one here? That's 1, 1.5. That's 1 and 3, 1 1/4, which is 5 pi and 4. Are we good? And down. Whoa, not good. It should end. And the other thing, you know how you've got 5 cos 4t, 4 periods fit into the normal 2 pi. Let's check. 1, 2, 3, 4. Okay? So your first graph. What's your second graph? We've got to differentiate that. Differentiate 5 cos 4t. What do you get? Differentiate cos, you get negative sine. So we've got 5 times negative sine 4t times 4. So we're going to differentiate it. We've got v, or x dot, is, yeah. So for the next curve, v equals 5 times negative sine 4t times 4. So therefore v is negative 20 sine 4t. What's the period? Now the other thing is, guys, all right, so a period is what? Yep, same as before. The period is pi on 2. We're not going to do every point up in there. What's the amplitude? 20, negative 20. All right, what's sine of 0? 0. All right, the other thing is the velocity curve is the gradient function of this. You know, you've got a stationary point up here, gradient 0, gradient 0, gradient 0, gradient 0, gradient 0, 0, 0, 0. So at all those points, all the maxima and minima, that's where you've got that your velocity curve passes through 0 at all your maxima and minima, because first derivative of displacement is velocity. Gradient of the displacement curve is velocity. So at all those maxima minima points, you're 0. Are we okay with that? So all those are 0. You've got to decide now, does it go down or up? I mean, I can do this by trying to sketch v equals negative sine 4t, or tell me about the gradient here. Negative. So this curve goes down. Does that? Velocity is negative. But you can just substitute some values in if you want. So you can go back up to that table, and when, do you want to go back up? We can go back up, just do the first few if you want. But guys, it is a negative sine curve, so it's down like that. Are you okay with that? Its velocity equals negative 20 sine 4t. The period's pi on 2, but it's a negative sine curve. Sine curve goes up like that. Negative sine curve goes down, so it will be like this. So, I mean, you can complete the table and do all the values, but from our 2-unit sketching of sine curves, we should know how to sketch that already. So, and knowledge of that velocity is gradient of the displacement curve. That's what that will look like. The other thing you can go up and do is go and fill up that table if you like. And what's this one? 7 pi on 4, I think. No, it's not. What's 1.5 and 2 is 1 3/4, 7 pi on 4. Okay. So, did you fill the table in or not? Or are you just drawing the graph? So either way, I don't mind. acceleration is the derivative of this other graph of the velocity curve. So differentiate that, and what do you get? Does the sign change when you differentiate sign? No, it doesn't. So you get negative 20 times cos 4t times 4. So therefore acceleration is negative 80 cos 4t, and that would be an amplitude of 80. What's the period again? Pi on 2. Cos curve is like that, but the negative cos, normal cos looks like that. What's negative cos? Where does it start? At the bottom. So the other thing is, because the acceleration curve is the gradient of the velocity one, well, you know where you pass through 0 at all the maximum minima of the velocity. At the, do you get it? See here, gradient 0 there, gradient 0 here, gradient 0 there. Do you get what I'm doing? That's gradient 0, gradient 0, gradient 0, gradient 0. So I can put all these 0 points on my graph corresponding to the maxima and minima of the velocity curve. So yes, it's the same points as the x graph. That's right. Yes, it is. Thank you. 3/4. Thank you. And this one too, 3/4. Sorry. What does that say? I can't even read that. 5. And that's 7. Because you just go by fractions. 1/4, 1/2, 3/4, 1. 1 1/4, 1 1/2, 1 3/4, 2. Sorry, don't know what I was doing. So trying to graph this, cos curve is like that, but negative cos curve starts from down here. So it would be like this. And notice that the period is pi on 2. And keep going. Now we are going to go and fill in these values because we want to go and look at this table up the top. We're going to put values in that table up the top. You okay, girls? Because I want to talk about that table. So when we fill that table in, we're going to notice some things, that when x is 0, so is acceleration, or for example, at some points. Okay? So I'm going to fill in the table up the top. Someone's going to have to help with your graph in front of you. Can I move or not? All right. Now, what have we got? So x, for velocity, the first one was 0, and then we had negative 20. Is that right? And then we had 0, positive 20, 0. And then we just keep going the same. Negative 20, 0, positive 20, 0. Negative 20, 0, positive 20, 0, negative 20, 0. And acceleration starts at what? What's acceleration start at? Negative 80, 0, positive 80, 0. Negative 80, 0, positive 80, 0. Negative 80, 0, positive 80, 0. Negative 80, 0, positive 80. So I'll just write down what those functions were as well. That was negative 20 sine 4t, and this is 80, negative 80 cos 4t. Okay, so, are we good or no?
Yes, we are.
Well, let's go back in. Why don't you fill this out, and we're going to look at the graph with that explanation now. So you know how you were writing this stuff out about displacement graph? Let's just have a look. You can write it if you want, or you can just understand it is fine. So displacement graph. The particle starts, how am I going to do this? I need to fold. Yeah, you can. You can, or you can just understand it is fine as well. So I'm folding this paper. Here's the displacement graph. Let's go. The particle starts at x equals 5. We good with that? It takes pi on 8 seconds to reach the origin. Is that good? It takes another pi on 8 seconds to reach x equals negative 5, because these go up by pi on 8s. It takes another pi on 8 seconds to reach the origin, or 0. And the particle repeats this pattern. Well, they should have gone back up here as well. But then the particle repeats that pattern every pi and 2 seconds. They have missed another pi and 8 to get back to 5. Dot, dot, dot. Oh, yeah, there we go. Yeah. The particle repeats this pattern every pi and 2 seconds. That's your period. Okay? The particle is said to oscillate from x equals 5 to x equals negative 5 about point O, which is the center of the motion. Okay? We good?
Yeah.
Now, velocity graph, sorry, I did this above the curve, but you can just do this here on paper. It's dx dt, which is 5 times negative sine 4t times 4, which we did before, negative 20 sine 4t. And the acceleration graph we did already, it's negative 20 times cos 4t times 4, which is negative 80 cos 4t. Now we're going to look at the relationship. So you had those written down before, didn't you? But you can write them down again in your book.
Wait, Miss, you know how you said the particles are to oscillate?
Yes. What does so when a particle goes from one position to the other, it moves from side to side, yeah. That's what oscillate means, going backwards, forwards, backwards, forwards, backwards, forwards. Or up and down, up and down, up and down. Okay?
Yeah.
Okay, so just get that down and
So you want us to write?
yeah, you can if you want. As long as you've got your velocity acceleration. If you understand what that is, I just write it oscillates from x equals 5 to x equals negative 5 about the point O. If you understand that, you don't have to write that other bit, but I'd definitely be writing about the oscillation. Is really, really important. So this bit in the middle is the fixed point or the center of oscillation, and the particle will go there, come back to the center, go back to the left, go back to the center. Oscillates forward and back. So at the end points, and you can come down to your graph, what's displacement at the end points? Where does it go? You can actually see it up here too. So this would be negative 5, 5. Are you okay? It goes 5 units to the right, back, 5 units to the left, back, or it could be up and down motion as well. 5 up, back to the center, 5 down, back to the center. And this is x is 0 in the middle. Okay? So you have your extremities of displacement obviously on the ends. That makes sense. Now, you tell me, when the particle goes to the end, doesn't it stop and turn around? Not that the ball goes and turns around, but it stops and goes back the other way. So you tell me what you think velocity is on the ends.
0.
And you think of a pendulum swinging. When do you think the pendulum's going to be fastest? Through the middle. Yes, it will be. It stops on the ends. It stops on the ends. So that was displacement. Pretty easy. In the middle, position 0, and the ends are just how far it goes before it comes back. On the ends, it has to stop. Tell me about velocity when it's traveling to the right. What's velocity here? Positive or negative? Positive. It stops. Then it comes back. Negative velocity, negative velocity. If you think of a swinging pendulum, it is fastest going through the center halfway back. So this is your maximum velocity. And in this case, what values were we getting for maximum? Now we're getting, I'm just putting speed actually, 20. Now when the particle comes back this way, that's the negative 20 because it's traveling left. Then it comes back to 0. Then when the speed coming back this way, it hits positive 20 in the positive direction. So x dot is positive 20, negative 20. Do you understand? The speed's always 20 meters per second or whatever the units might be, centimeters actually per second, but the velocity heading to the right, it's positive 20 meters per second. Heading back to the left at that center point, it's negative 20 meters per second. But the main thing you need to know is on the ends it stops, and through the middle, you always think of a pendulum. It's going the fastest. It's like pushing a kid on a swing, but they've got to be going the same height every time. They're going fastest on the way through, the closest to the ground. Then they go back up and they slow down, sort of. All right, now on the ends. Now the acceleration, guys, this is what we've got to look at. Say we start at the origin. When the particle's moving like that, isn't velocity positive? And when the particle comes back this way, the velocity is negative. Also over here, when the particle's moving that way, positive velocity. And when and on this side of the origin. So the particle will start, let's say it starts here. Positive velocity, stops, negative velocity. But guys, I'm interested in acceleration as well. Girls, if this particle is going this way to the right and it stops, tell me about acceleration. Why did this, if I'm pushing it from behind, it'll keep going. So acceleration must be acting to the center. Negative acceleration. Otherwise, that particle, if it's being pushed, it'll keep going. So why does it stop on the end? Because acceleration is acting towards the center. Now, when the particle comes back down, where's the fastest bit of motion? In the middle. So it's being pushed. For the velocity to increase and get faster and be fastest in the middle, it's like you're pushing it. Acceleration, again, is to the center. So positive acceleration, positive velocity here, negative acceleration. That's why it slows down and stops. It then comes back this way. The velocity is in the negative direction, but it's speeding up, so acceleration is also negative. Do you notice that acceleration is acting towards the center? Now, in the first sentence you wrote, we'll just do this side as well. So what about here when the particle is here, it stops, it comes back. Does it speed up? Yeah. So acceleration is also this way, but it's in the positive direction. So if this particle stops on the end and gets fastest, and it's fastest here in the middle, it's being pushed. It speeds up. So velocity is positive direction, acceleration is positive. So here, and then acceleration changes to negative, and that's why it slows down. And then it comes back and it speeds up. So velocity is negative, so is acceleration because it's speeding up. But once it hits the center point and goes back here, isn't it slowing down again to stop here? So acceleration's got to be in the opposite direction to the velocity. So look at what I've just drawn. For this to be going here, negative velocity, but it slows down and becomes zero, acceleration has to be that way. Look at my 4 arrows with A. They're all acting towards the center. So girls, if you've got positive acceleration, and then all of a sudden I've got negative acceleration, on a number line, when you go from positive to negative numbers, you must pass through 0. Let's look at your acceleration graph at, for example, the center. Let's look. Well, look at this. When x is 0, look here.
Your x doesn't always.
No, it doesn't. No, we're just doing the simplest case. We're doing the simplest case. It won't be 0 when we go 5 cos 4t plus something. Yeah. Okay, so, but just notice at the center of motion, our displacement for this particular graph is 0, so is our acceleration. So the acceleration is 0 in the center. I suppose it's deciding what it's going to do. I don't know. No, it's going from positive to negative acceleration. So, guys, yes, yeah, it will be. So, because it's going from positive to negative acceleration. So acceleration always acts towards the center, and we wrote that. Simple harmonic motion occurs when a particle moving in a straight line so that its acceleration is always directed towards the fixed point, which is the origin. That was the first sentence you wrote. You wrote it with no idea what it meant. And now hopefully you can see that acceleration is always acting towards the center. That is really, really important. Okay, now acceleration graph, it's a max on the ends. So do we have, but the thing is when it's positive 5, we've got negative 80, because see how we've got negative acceleration here, negative acceleration, that's the negative 80. And over here I've got the positive 80. So when the displacement's negative, the acceleration's positive on this side. You can see from the graph. I'm going to put the 3 graphs down there. Look up here. Positive 5 for displacement, negative 80 for acceleration. So on the end we go plus 0 minus. On the end points. Minus 0 plus. Plus 0 minus. The displacement and the acceleration will be opposite signs at the end points of the motion. Guys, this is really, really important. You know that it stops on the end. So just notice the change in sign here. But you'd see it in the graph anyway. When you look at the graph, look, positive 5, negative 80 for acceleration. 0 for velocity. All right? So the main things, acceleration is always towards the centre. At the endpoints, you have your maximum displacements, be it positive or negative. At the endpoints, it stops. Think of a kid on a swing or a pendulum. It stops and goes back the other way. But acceleration is always directed towards the centre. If the particle's speeding up, it's like acceleration is pushing, acceleration is in the same direction as velocity. If the particle's slowing down, acceleration is in the opposite direction of velocity. And in the middle of the motion, that's when you're travelling the fastest, and when acceleration is 0 in the middle as well. Okay? Why is the acceleration at 0 in the middle? Because it's going from positive to negative acceleration. Can't go from a positive to a negative number without passing through 0. Please copy this. So consider a pendulum. Here x is negative a, x is 0, x is a. Draw it like that. On the ends, we're going to fill... On the ends, what happens? It stops. X dash is 0. X dash is 0 there. And in the centre, it's the fastest. X dash is max. I'm just going to put maximum. All right. And acceleration, x double dot, always acting towards the centre. Always. So if you're on the left, it's acting there to the right. And if you're on the right, it's acting to the left. Acceleration is always acting towards the centre. We did that here, look. Acceleration there, there, acceleration there, there. It moves the fastest. The particle is, no, the velocity is the fastest, maximum speed. I'm just going to put maximum speed in the middle. Makes sense? Maximum speed in the middle, so copy those. Consider a pendulum, etc. Maximum speed in the middle. Oh, and can we put that acceleration is 0 in the middle? Right. So, displacement is always to the same points if there is no air resistance. All right. When you push a kid on a swing, they don't go forever because there's air resistance. All right? Yes. Motion is symmetrical about the centre of motion. This is all assuming no air resistance. Particle is slower on the way... Wait a sec. I'm missing a word. Wait. Particle is slower on the way out and faster going back in. You know when you go to the... Think of a kid on a swing. They slow down as they're going up. They speed up when they come back down. So particle is slower on the way out, faster on the way in. And this just shows the relationship between V and A. We did this before, but if velocity is positive and acceleration is negative, you're slowing down. If velocity is negative, acceleration is negative, you're speeding up. That was that way. If velocity, you know, from the centre out, so this is the centre of motion there. You know how you're slowing on the way up when the kid on the swing, pretending no air resistance? Why are they going slower? Velocity is positive, acceleration is negative. Coming back in, velocity is negative, acceleration is negative. Going back out from the centre, velocity is negative, acceleration must be positive. That's why they're slowing down. And the last one, coming back in, velocity is positive, acceleration is positive. That's why you speed up. So acceleration is always working towards the centre of motion.
What does it say after way?
Way out. Particle is slower on the way out, faster on the way in. So if you didn't get that all down, please just get it in the video. The homework is just to finish off